we are going to pick up with 8.3. This is about rational functions and their graphs. Again, the PDF for these notes is on the portal if you want to go in and print those before we get started. Okay, so rational functions, this is a continuation of reciprocal functions, but the definition of a rational function is a function that involves division or a quotient. Okay, so this is a kind of a complicated way of saying there's just a fraction involving two functions with an x in the numerator and the denominator. Okay, so just like we talked about with the rational function with the inverse function, in a rational function, q of x, meaning the bottom part, cannot equal 1. Okay, so we have to keep that in mind. That's going to change some things about the graph, and we'll see that in just a minute. So below are 3 examples of different types of rational functions. They can have different forms, okay? So this first function, if I were to graph this, it would kind of be pretty funky. It would look like that, okay? For purposes, for what we're going to get into in a minute, I'm going to call that graph A, okay? This next graph, you wouldn't think it, but it's actually a line, and it has a hole in it at 2. And again, we'll get into why that's happening in a minute. I'm going to call that graph B. And then this last graph is going to look like the rational functions that we've studied before with an asymptote at 2. Okay, and then I'm going to call that graph C. Okay, so all those are rational functions because they have that format where we have 2 different parts being divided, both have an x. Okay, so these 3 types of graphs can fall into one of 2 categories, continuous or discontinuous. So graph A, so if we think about it, graph A, this is called a continuous graph because as I look, there's no jumps, asymptotes, there's no holes. Like if I look at graph B and I see that hole, those are called continuous functions. So graph A is continuous because it has no holes, jumps, or skips. And if I think about an asymptote, that is a skip because the graph skips over a point. Okay? And then graphs B and C are the other type. They are discontinuous. And I can easily see why that is the case because if I look at graph B, there's a hole. It skips over 2. And then the last one has an asymptote, which is a skip. Okay? So these are just the opposite of continuous. Okay? All right. Now we're going to talk about points of discontinuity. Okay? So if you remember that second graph had a hole at 2, that's called a point of discontinuity. Okay? So these are points that make the denominator of a function equal 0. Okay, so what I mean by that, if you think about that, if you think about the function f of x equals 2 over x minus 1. Okay, so the point x equals 1 would be called a point of discontinuity. Is called, I'm going to abbreviate this POD, point of discontinuity, because when I plug in 1, so if I were to plug in 1 right here, I would get 2 over 0, which is a no-no. I can't have that. Okay, so therefore, that point where that happens is called a point of discontinuity. Okay, so there's 2 types of these. So there's a removable POD, point of discontinuity, and then there is a non-removable POD. Okay, so let me give you two examples of when this would happen. So a removable point of discontinuity is when you have a rational function that has the same pair of linear factors in the numerator and the denominator. So what I mean by linear factors is like set of parentheses. So if I look right here and see that, okay, I have x plus 2 and x plus 2. They technically cancel out, but on the graph, there's going to be a little hole at x plus 2 because I can see that in the denominator, if that's going to equal 0, -2 is going to be a point of discontinuity, but it is removable because technically it would cancel out in the original function, okay? And then non-removable means that it can't cancel out. So an example of that would be like x plus 4 over x plus 2. So in this case, again, if my denominator were to equal 0, I would have a point of discontinuity at -2, but it is non-removable because it can't be canceled out with anything in the numerator, if that makes sense. So removable versus non-removable. Okay? All right, so how do we figure out where these points are? Okay? So what we're going to look at in each of these examples is what the domain is, how is that affected by any points of discontinuity, and then if those points of discontinuity are removable or non-removable, okay, and then what are the x and the y intercepts, okay? So looking at this first function, again, I'm asking myself, what value of x makes my denominator equal 0? That's where the trouble happens, okay? And if you think back to what we did in chapter 4 when we factored quadratics, we're going to be using some of those factoring techniques here, okay? Because I can see that in my denominator, that is a factorable expression, meaning there is a value, or there are values for which they are a product that equals 3 and they can add up to be -4. So if I think about what those are, -1 and -3 would work here. So that means this expression is going to factor into x minus 1, x minus 3. If you aren't the strongest with factoring, I suggest you go back and watch some refresher videos on that. Let me know if you need some help because we just don't have time to get into that right now. Okay? All right, so looking at my expression here. Did I type this in? Oh, well, I think I may have had a typo right here. You know what? This top, this should be -3. My apologies. So let's rewrite. This should be a negative right here. So this is negative. So I have x minus 3. So I have x minus 3 over x minus 3, x minus 1. There we go. Okay. So I can see that, oh no, let me undo that. I can see that x minus 3 and x minus 3, those linear factors will cancel, okay? So this means for x minus 3 equals 0, x equals 3 is going to be a removable point of discontinuity, okay? So I actually have 2 points of discontinuity because I also have x minus 1 over here, so let's also find that one, but it will be non-removable. So I've got x minus 1 equals 0, so that means x equals +1 is a non-removable point of discontinuity, okay? All right, so we found all the points of discontinuity. Now we are going to look at our domain, okay? So the domain is going to be everything except these 2 points that I just found. So it's going to be all reals, but x cannot be 3 and x cannot be 1 because those give me a 0, okay? And then my x-intercepts, okay? So to find my x-intercepts, all I'm going to do is set my numerator equal to 0, okay? So I'm going to have x minus 3 equals 0, so that means my x-intercept is going to be at 3. And then for my y-intercept, I'm going to make all the x's zeros. Okay, so that means I'm going to have y equals 0 minus 3 over 0 minus 3 over 0 minus 1, which is going to be negative 3 over negative 3 times negative 1, which is going to be negative 3. I'm sorry, negative 1. I'll write that last step so we can see that. So we're going to have negative 3 over positive 3, which is negative 1. That's my y-intercept. Okay? So what I want you to do now is pause the video, attempt number 2, see if you can factor the bottom. If not, there are no points of discontinuity. So go ahead and try to do number 2. All right, so this one actually, if we were to ask ourselves, can we factor x squared plus 1? The answer is no. And then again, is there any value for x for which that can be 0? And that is no. So what this means is there are no pods. There's no point of discontinuity, okay? Which means my domain is going to be all reals. This is going to be a continuous function. My x-intercept, again, I'm going to set my numerator equal to 0. So I'll have x minus 5 equals 0. So x equals 5 is the x-intercept. For my y-intercept, I'm going to set all of the x values equal to 0. Okay, so I end up with 5 over 1, meaning that y-intercept is 5. Okay? All right, and then this last example. All right, so again, we're looking for points of discontinuity, how that affects the domain. So let's see if we can factor anything in this expression before we start finding those. So in the numerator, I've got x squared minus 3x minus 4. So if I factor that, I'm asking myself 2 values that multiply to give me negative 4, add to give me negative 3. That would be negative 4 and positive 1. So this is going to factor into x minus 4, x plus 1, and then x minus 4 on the bottom. So I can already see I'm going to have a point of discontinuity at x minus 4. The question is it removable or not? Well, it can cancel out with this, so that means it is removable, okay? So I have a point of discontinuity at x equals 4 because x minus 4 equals 0. When I solve it, means x is 4, okay? And this is removable because I could factor it out since there's also that factor in the numerator, okay? So what is my domain? My domain is all reals except x equals 4, okay? My x-intercept, remember I'm setting my numerator equal to 0. So when I do that, I get x is 4, x is negative 1. And then for my y-intercept, I'm going to plug in zeros for all the x's. So I've got 0 minus 4, 0 plus 1 over 0 minus 4. So that's going to give me negative 4 times 1 over negative 4, which is 1. Okay? All right, so I'm going to go ahead. That's the end of this video. Again, I'll upload this as the 8.3 video on the portal. Finish up your assignment sheet. I would try to kind of chunk that, maybe work on each section for about 20 to 30 minutes a day. And we will have a quiz on these 2 sections when we come back next Tuesday. And I can't wait to see you guys in class, hopefully. We'll see.